having them in the beta test this year. So I will skip this. Probably not so interesting. And this is a HGCal module prototype that we actually used in last year, which again, you see that you need to have a structure that you can protect your detector and then read out. So the base plane will be the absorber material, like tungsten or copper, depends on what you want to do. Then you have a layer of protection or contact. Then you have your sensor layers, another layer that to glue your PCB. So for example, from this is a base plate, you put the glue on, you glue the cap on, and then put on top another glue, then you put the silicon. Then you put another glue, and put the PCB on it. Okay, and this was a test bin, happened last year, and it's a bin area, and since this is my presentation, I choose a picture that has me in it. So this is the first test bin that we have single layers, and then the second test bin we have 8 layers. So this is just built, this is our poster. And we're very lucky. The first morning we take data, we already see electrons right in the middle. And this is me showing all the young people, student postdoc, how to take data. And here just a couple of plots that show you what we have been doing very well. So this is 8 layers that, for example, if you muon pass through, because muon is minimum ionizing, you see very quiet detector everywhere with one path or one channel having the signal. But in case of electron, because the absorber we put in front of silicon, it starts creating showers. You can see the shower become larger, but as soon as the shower start development, it loses the energy. So you see it dies out, then you get nothing. That means the electron is stuck in the middle of the detectors. And then by measuring this, you can first you can do a very good MIP calibration. So because you know what the energy deposit, you can calibrate it, and then you can measure the total energy. You can see mapping different incident particle, incident energy of the electrons. They scale up very nicely. Okay, and then for the test bin this year, for the last year we only have a segment that is for the electromagnetic handicap only. Now we want to build more realistic, so you have 3 parts. The first test bin will still be the EM only or EE only, and the second test bin in June we have 2 layers with the front hadronic. So still silicon but different absorber. And because the shower development, you also want to have a larger coverage to cover all the hadronic shower. In the third layer, we actually going to borrow the Calais chamber, hadronic chamber, to act as a back hadronic chambers. Okay, so much for the hardware. I'm just going to show you what we expect for the physics. There are many physics. We have studies, but I will just show you the Higgs since this is the one our group has been working on. And needless to say that you probably have heard a lot. The Higgs in standard model Higgs is needed and then introduced to explain the electroweak symmetry breaking. And it's a very unique scalar particle, spin 0. And so by interact with the W and C, you get the mass, and the mass of the boson or the fermion is proportional to the coupling of the Higgs. And so Higgs was awarded the Nobel Prize, part of our effort in LHC. And since we want to understand the fundamental nature, we need more data and precise measurement. That's why we need the high luminosity LHC and CMS phase 2. And so far, the Higgs is observed produced like standard model particles. This is, for example, all the production mode, like 2 gluon fusion into the Higgs, or vector boson scattering. And this is what the ratio of the production with respect to standard model. So you see they are very close to 1. So you produce like it, you also decays like Higgs. I like standard model. Sorry. And for example, this is the coupling constant, coupling for the different particles, and they measure the particle mass. So you can see that their standard model is predicted, but they all have large errors. So one thing our group has been working on is the Higgs to gamma gamma. The reason is that we build the HGCal in the CMS. Of course, we try to work on the electron photons. So this is a quick summary how the analysis happened. So you want to find the 2 photons in the CMS and to build the Higgs. So first thing is you try to build sort of the photon ID that we use the boosted discrete multivariate analysis, that you build a response, and the photon will be, or the photon from Higgs should stand here while the background is standing here. So you see they are separated somehow with some power. Then once you have this, there's a second BET that's built by combining the physics, like the acceptance and the kinematics of the photon from Higgs. Then you see that for the background, it looks like this, but the standard model Higgs will peak at 1. So by doing the category, you can have the region that has better signal-to-noise ratio and have a better potential sensitivity. So once you categorize them, you start looking at the diphoton invariant mass. You have anomalous QCD background because QCD produce diphotons from the scattering that is irreducible, but on top of that, you get to see the Higgs. And here's the Higgs significance. So at 2012, we have accumulated enough data to claim the discoveries. And there are also special categories that you can distinguish them from different productions, like a TD bar Higgs by requiring B-jets, or the vector boson Higgs associated production, or the VDF by looking at the 2 forward jets in the events. So here is what we have with the Higgs gamma gamma and CMS only, and with respect to different production. So you can see that they all considered with 1, but they all have large error. So gluon fusion, they have like 30% error. So what we want is, at the time of the end of high luminosity LHC, we can reach up to %. So it's 10 times smaller uncertainties. And then other coupling constant we want to measure. So I make an example is that the thing you measure, for example, Higgs gamma gamma from gluon fusion, is actually a combination of the production times the Bragg refraction. So he has the mix of the gluon coupling and the photon couplings. And you can imagine all the decay, all the analysis, like Higgs to ZZ and Higgs to BB bar, they all have a mixture of multiple couplings. So what you do is you have all the analysis channel, and then you try to figure out the coupling inside there. You do a simultaneous fit for all the results, so that you can get what the coupling is to the W and Z top quark, B quark, and tau, for example, neons. And now it's consistent with one with large error, like 10% to 20%. This is what we want to achieve on the end of high luminosity LHC. So you see that everywhere 2%. And this is another plot that I've shown earlier. The other one was combination of alphas and CMS. This is CMS only. So you see every particle still have large error uncertainty on the coupling. But at the end of the high luminosity LHC, you can see that it's almost invisible. It should be at the % level. Okay. And these are the similar projection for each decay modes, where the Higgs gamma gamma, that we'll keep working on it. One thing that I also want to mention is the Di-Higgs production. This is special is because when you measure Di-Higgs, it directly probe the Higgs coupling, since the production is the coupling of the cube. So it's the direct measurements. But the problem is in the standard model, this production is very small. And so you have to accumulate a lot of data. For example, this is what we expect in the end of high luminosity LHC, and the red one is the Di-Higgs to BB gamma gamma. I think we can probably reach 2 sigma, and if we do something smarter, maybe we can do better. But this is so far what we think we can achieve. Some other honorable mentions. I don't think I have too much time. There are also many other interesting physics that can use more data, like MSSM, Higgs to gamma gamma. So this is what the exclusion region now. This is what you expect the red in the end of high luminosity LHC. And for example, the top quark mass, we should be able to reach smaller than 0.1%. B sub s to phi phi that can measure the CP. And for example, this is the invariant mass for the phi phi. And one thing that can be done after phase 2 is that in the level 1 trigger, that means when you take the data, you make a decision if you want to save this event or not. You have a track triggers. That means you can identify 4 tracks that forms a beam. So you can save the event. Also other analysis like dark matter to monojets and the Z-prime to lepton pair, top pairs. All these things will have, so I have the plot. For example, the V to EE, you see that you exclude up to even 5 TeV, depends on models. Okay, so here's my summary. CMS has been performed very well, and the silicon detector technology has played an important role, especially our group has developed and contribute on building 2 silicon detectors. And we are aiming to build the 3rd one, the high granularity calorimeters, which even larger scale, larger size, and we're preparing to be complete. And the high luminosity should start, high luminosity HGC should start 2025, and last for 10 years. And we will get more physics out of it. And the last one I want to mention is, after that, this are the proposals that is on the table for discussion. After 2035, there might be a new collider in China, or the linear collider in Japan may happen, or some may feel that they want to take a leading role and then build another 100-kilometer collider. We don't know. But one thing for sure is the silicon-based detector, not only calorimeter, maybe tracker, that will still be the key components, and we think we should try to grab it and having something important on campus. That's all I want to say.
Okay, I think we can have more questions for this session.
Actually, this one, I want to guess how much it costs. This is a pixel detector. On book, this costs 3,000 Swiss francs. This one.
How much?
3,000 Swiss francs. That's 10万台币. Just this.
10万.
How many was that in weight?
Almost 2,000.
3,000.
I have the number here. Even just barrel is almost 1,200, and then there's NCAP plus spares.
Any question?
So how would you compare the future plans that you mentioned in Japan, in China? I mean, basically, you can compare them in different functional aspects, like in terms of scientific goals, or say their efficiency, or cost.
So
how people, I mean, this is a general question about how people feel about it, because people have been talking a lot about it. Even early on, maybe 10 years ago, Fermi is talking about their linear collider, but perhaps the plan is no longer there.
16.
They are 16 years ago. So
I think linear collider has more defined physics, which is the Higgs physics. And from my point of view, the circular collider, especially the CEPC and HGC, because they are large, their potential to switch to become the hadron colliders. So they are not only can do Higgs physics, they can do searches after they've done the Higgs. That's what I see.
The question is the money.
So say if you are going to get evening amount of money, then which one will be the best proposal? The one in China, the circular big one?
I think for the long term, yeah, I will bet on circular. Because so the idea of CEPC, I think everybody knows, it's not a secret, they want to copy CERN experience.
Yeah,
because CERN start from the lab, and then lab is E plus E minus, and they use exactly the same internal. So then the new magnet become the LHC hadron colliders. And the CEPC can do the same. They can finish the EE as a Higgs factory, then become PP.
So maybe you can go to page 48 just to make it clear. I think the CERN circular collider and the Chinese circular collider, they are competing.
Competing.
Yeah, they have the same, almost the same design.
But the one you have to build it in Geneva area.
So you are looking.
Kind of expensive.
So you are looking for some experimental evidence that something that is not consistent with the great unified theory, right? Is there any so far?
The standard model,
Yeah.
so far, no.
So far, so
everything is still consistent.
Boring.
So you are hoping there will be something.
True, every happy people trying to get
It's not the
something.
great unified.
I'm sorry.
This is just the
Standard model, standard model, not that great.
Okay, standard model.
Yeah,
Okay.
that's correct.
So any indication there's, what are you expecting, that higher energy, some new particle will appear? Or if you have more,
So-
events that, the analysis will be different or whatever?
I think two things we know we have to search. One is SUSI, although it's very difficult to be ruled out. The other is stacked dark matters. Because, for example, Ding has shown there's 1 TeV dark matters. So we're already saying that then LHC should see if we understand the production mechanism, we start to see. But these are the two things that we should see. But of course they are unknown, so we don't know what's gonna pop out.
Okay.
Well, you had emphasized on precision Higgs physics. So what about it? I think this is a partial thing that
Yes.
to
Yeah,
educate our physics department chairman, right?
I think the direct search is always novel and attractive, but precision measurements will bring you hints if they are not consistent with the model. For example, if you measure up to %, you see they are not consistent, you know there has to be new physics. And there are several analyses which are very sensitive to new physics, like in the loop calculation, you have if you have new physics, it goes in, you raise your production by 100 times more. That will we'll see in the precision measurements.
Can you go to page 44? On the lower right figure, you did not show the mu error. But
So-
it looks suitably precise on the upper right figure. So can you explain?
That's probably not from the direct observation. From the top, yes. Because Higgs to mu mu is rare decay. It's not even observed yet. And yeah.
Right. So what does that?
So this is from the indirect fits. So I think this one, yeah, you get it once you observe it. You can shrink the observabilities once you
So
observe.
that would be a direct observation.
Yeah, it's a nice
So that tells you the importance, right? Not just the other ones as well, but
Yeah, this. Yeah, we don't have the observability.
okay. This is not. This is a point of discussion. If you look at the left-hand upper left figure, the one labeled with mu,
Okay.
it's not inconsistent, but we have practically no knowledge. Whereas on the right-hand upper right, say the mu one, is just not accessible right now.
Okay.
But with a much larger data set,
You
if it also falls on that line, yeah, it looks pretty boring, but we're hoping it doesn't. But there's potential, that's
should be
all.
able to. Yeah, sure.
Go to the next page. This 3,000 inverse Fedorban expectation, right?
Yes.
So according to this simulations, so we can this is the what's that?
This is like
Two Higgs, right?
Yeah, 2 Higgs and
So
one
with
of
this
Higgs.
signature, you say I say in your talk, you say it's only 2 sigma.
Yeah,
It's
because
written there.
the orange is resonant background. Only the red one.
Oh,
So you have to decouple.
Okay, it's 2 Higgs. That's right. But
So Friday, this is partially an answer to your question. The 2 sigma means that the LHC is not designed for this kind of physics.
Yeah.
Whereas a linear collider with sufficient energy,
They'll be doing better.
we will be able to measure that fundamental coupling. So they are complementary.
Otherwise, you cannot measure the Higgs potential. This measures directly the
Yeah.
nice Higgs potential we know from superconductivity.
So I would say, he's been focused on hardware all this time. But the reason he's put there to work very hard is because these are fundamental. Okay. If you go back to the particle table, particle
Higgs.
table, it's close to the end. We've known every particle, and this Higgs boson is a new kid in town. So I would say humankind just has to study, beat the horse to death, and go on with it. So that's what we're trying to do. And start to get related to you, right? If that triple Higgs coupling or this Higgs potential you understand better, it relates to the early universe.
That's
for
right.
sure.
Yeah.
okay.
Do you know how to measure the hypercharge and the isospin of Higgs? Hypercharge.
Don't know.
Anyone?
May I ask a very simple question?
Sure.
Why you choose granularity to get at HGCal? I mean the word granularity.
It means it's very finely segmented, so you have a good precision.
Can you elaborate?
Uh,
It's a student question, so you should always be even
So-
more attentive to students.
So in the old time where we use crystal, that means then you have a limitation. So you don't want to make it so small that you cannot handle or too expensive. So if you have at least large of the crystal in the cross section, once you measure something, you don't know where it enters. So you only have a special resolution on this size, like centimeters. But once you switch to silicon, you can make the pad very small, like millimeter level, and because of also the shower in there, so you don't measure single channel. You have like if you have 2 channels, measure one thing. By doing the weight, energy weight, you know that, for example, if these 2 channels have measured exactly the same energy, you know the incident particle should have to be exactly in the middle of these 2. And if they are different energy, you can start correcting your incident particle positions. So that's why you have much better spatial resolution.
We've never done this before.
Yeah, this is the
This
first.
type of detector,
This design is really new, and yeah, it's not been done before. To measure showers using silicons.
All right. So if there's no question, let's send Dr. Liu again. Feel free to ask him a question in private.
Or just come to see my detector. Not a main.